Go ahead.
Um, Good afternoon, everyone. Today, I'm gonna talk about universal solutions in temporal data exchange. I'm Zehui Cheng. This is joint work with my advisor from King Collatus. This paper brings together two different areas, data exchange and temporal databases. Data exchange is a process which transforms data structured under a source schema into a data structured under a different target schema. Data exchange is formalized using schema mappings in the above paper by Faggin, Collatus, Miller, and Popper. Schema mapping is a tuple, consists of a relational source schema S, a relational target schema T, and a set sigmas of constraint between S and T. There are two common types of the constraint. The first one is source to target tuple generating dependencies, which we call STTGDs for short. The second one is target equality generating dependencies, which we called target EGDs for short. Both of them are formalized in the first order logic. Here are two examples of those two kinds of constraints. The first one is an STTGD, which asserts that for each employee works in the company C at position P, then there exists a salary for that employee. The second one is a target EGD, which is also a functional dependency. This is saying that the position determines the salary. Data exchange problem asks, given a source instance I, find a solution for I that is a target instance J, such that the pair ij satisfies the constraint sigmas of M. In general, there are many solutions or no solutions. Universal solutions are introduced as the most general solutions in the above paper. The notion is formalized using homomorphisms. Then, universal solutions have become the preferred semantics. The other area is temporal databases. There are two different models to describe temporal informations. The first one is abstract model of time, where temporal information is represented by time points, which are natural numbers. The second model is concrete model of time, where temporal information are represented by time intervals, which are closed open intervals, such as S to E. Temporal schema is a schema with temporal relations, such as a relation R with attributes, name, company, and a temporal attribute, time. Under temporal schema, there are two different types of instance. The first one is abstract instance, where temporal attributes range over time points. The second one is concrete instance, where temporal attributes range over time intervals. For each concrete instance, we can convert it into an abstract instance, which carries the same information by semantic function, which converts all tuples of the form mu with time interval S to E into a set of tuples with time points range from S to E. Here is an example of the semantic function. Temporal databases and data exchange has been studied independently in the past decades. That was only recently put together to be a topic of temporal data exchange. Temporal data exchange is formalized using temporal schema mapping, which is a tuple M, consists of a source temporal schema S, a target temporal schema T, and temporal STTGDs, and temporal target EGDs. Given a concrete source instance I, by using semantic function, we can produce an abstract source instance which we called bracket I. In general, one hopes that to use a standard data exchange, we can generate an abstract target instance, JA, which is an abstract universal solution for the bracket I. Then in the concrete model of time, we would like to produce a concrete target instance J such that the semantic function of J, which we call bracket J, is also an abstract universal solution for the bracket I. Hence, the bracket J and JA are equivalent up to homomorphism. Then we call such J is semantically adequate for I. And we call this is a property of semantic adequacy for the temporal schema mapping. Then the next question is, can we produce a concrete universal solution J such that the concrete universal solution J is semantically adequate for I? To answer those questions, there are several challenges to be overcome. In data exchange, universal solutions are produced using the cheese algorithm, which introduces labeled nulls to witness existentially quantified variables Y in STTGD. While in temporal data exchange, temp-stamped nulls need to be introduced to witness existentially quantified variable Y in temporal STTGD. However, managing temp-stamped nulls requires special care when it comes to target constraints. This becomes a challenging problem when multiple temporal variables are used in STTGD. The very first paper on temporal data exchange is a recent paper by Goshinara and Chomsky. They considered a restricted class of temporal schema mappings, in which every relation symbol in S and T has one temporal attribute. And the sigma ST is a set of STTGD. Sigma T is a set of target EGDs. Each constraint in them contains exactly one temporal variable. Hence, the only temporal variable occurs in every atom of the consequent of STTGD. And no temporal variable is existentially quantified. Here is an example of the STTGD and target EGD in the temporal data exchange. Then they have proved the following theorem. Let M be a temporal schema mapping as above. There is a polynomial time algorithm such that given a concrete source instance I, if a solution for bracket I exists, then the algorithm produces a semantically adequate concrete target instance J for I with respect to M. If there is no solution for bracket I, then the algorithm fails. However, they did not address the question of whether there is always a concrete universal solution that is semantically adequate for I. To address this problem, in our paper, we firstly identified a temporal schema mapping M star and the concrete source instance, for which there is no concrete universal solution that is semantically adequate for the source instance. And we proved the following theorem. There are a temporal schema mapping M star with one temporal variable in each constraint, and a concrete source instance I star, such that there is a concrete universal solution for I star with respect to M star, but no concrete universal solution is semantically adequate for I star. There is a concrete universal solution for N of I star with respect to M star, but no concrete universal solution is semantically adequate for N of I star, where N of I star is a normalized version of I star, computed in the first step of Goshinara and Chomsky algorithm. Here is our schema mapping M and the source instance I. Please observe that in our target EGD, there are two temporal atoms here, which is a source of the problem in the temporal data exchange. Then we have been able to identify a class of schema mappings for which there is semantically adequate concrete universal solution for the source instance. We prove the second theorem. Let M be a temporal schema mapping where both the source instance, source schema S and the target schema T contains temporal relations and non-temporal relations, such that each STTGD contains at most one temporal variable. If an STTGD contains a temporal variable, then that temporal variable occurs in every atom of its consequent. Each target EGD contains at most one temporal atom in its antecedent. It may contain non-temporal atoms. Then there is a version of Che's algorithm, such that given a concrete source instance I, if a solution for n of I exists, then the algorithm produces a semantically adequate concrete universal solution for n of I. If the algorithm fails, then there is no solution for the bracket I. Note that the semantic function of I equals to the semantic function of n of I. Then after talk about temporal data exchange with single temporal variable, it is nature to think about temporal data exchange with multiple temporal variables and comparisons between the temporal informations, such as Allen's relation on time intervals, meets, overlaps, and so on. For instance, the time interval 2010 to 2013 overlaps with time interval 2011 to 2014. If we allowed multiple temporal variables, then the concrete STTGDs and concrete target EGDs are formalized in the following forms, where the pi and the rho are Boolean combinations of Allen's relation. Then we have some results about a restricted class of temporal schema mappings with multiple temporal variables. What is the restricted class of temporal schema mapping? That is a concrete schema mapping such that each STTGD is full and each target EGD contains contains at most one temporal atom. An STTGD is called full when there is no existentially quantified variables in the STTGD. Here is an example of the full STTGD. Then there is a polynomial time algorithm, such that given a concrete source instance I, if a solution for I exists, then the algorithm produces a semantically adequate concrete universal solution J for I with respect to M. If the algorithm fails, then there is no solution for the bracket I. In fact, we have some other results in our paper, but that's all I want to discuss in today's presentation. This brings to our concluding remarks. We firstly show that semantically adequate universal solutions may not exist even for temporal schema mappings with single temporal variable. Then we identify a class of schema mappings with single temporal atom in each target EGD, for which semantically adequate universal solution exists. Finally, we expand the original framework of temporal data exchange studied by Goshinara and Chomsky while considering temporal schema mappings with multiple temporal variables. There are many problems remain open. The most important one is to study temporal schema mappings with existentially quantified temporal variables. This completes my presentation today. Thank you for your attention.
Thanks, Zehui. So let's see whether from the audience there is any question. You can unmute yourself and you can try to make a question if you like.
Okay. So the question will be in the chat, right? Or...
No. So people can unmute themselves and they can pose questions.
Okay.
Otherwise, let me start and try to make a question. Whenever you say that your algorithm is able to find this this universal solution in polynomial time, this polynomial time is, let's say, based on the data, based on the constraints, is a combined complexity. What do you mean here in this case, polynomial?
It is actually based on the database.
So it's, let's say we can say just data complexity, so the constraints do not play any role.
Yeah.
And do you know what is the combined complexity in case we consider also the constraints?
Can you repeat the question is?
So what about if you consider also the constraints playing a role, being considering the complexity? Is still polynomial in the size of the constraints plus the data, or is the
so if we consider the size of the for example the number of the variables in our constraint, then the complexity could be the not polynomial, exponential time.
Okay, so combined complexity would be exponential.
Yes, Alessandro, if I may add something to this, already in the case of standard data exchange without temporal, without time, already there we know that the complexity is p-space hard in general.
Okay.
Yeah, it's exactly what you pointed out. It's the trade-off between the data complexity and combined complexity. Yeah, and we have worked this out in the context of standard data exchange. It has not been done yet because this is an emerging area, the temporal data exchange.
I see. And if I can have maybe a second question, which is in the case in which you have these multiple intervals, you use these Allen relations. Now, since actually these temporal databases are essentially based on points, so this coalescing is just, the intervals are just for coalescing purposes, I'm wondering whether a better result can be obtained by, instead of using Allen relation, you can use some point-based relation. And then obviously in this case, this universal solution must be found on the abstract representation of the databases.
So now in our concrete model of time, we choose Allen's relation, but we transfer the concrete STTGD and concrete target EGD into the abstract STTGD and target EGD. There we have time points relation.
Okay, so you transform the Allen relation into point-based relation. Okay, so.
And this does not show up in the Golsanara-Homiki work because they had a single temporal variable. Therefore, the temporal TGD could be interpreted either as over concrete time or over abstract time. It made no difference. But when you have two, you have to do the translation.
Yes, whenever you have two, you have to start. Yeah, I agree. Okay. Other questions from the audience? No, otherwise let me thank again Zehui, and let's go back to let's go now to the second talk.